Welcome to Lecture Online, and in this next video we're going to explore stress and strain a little bit more. In this case we're going to talk about what we call either tensile or compressive stress and strain. So in this case here we have a bar and we're pushing on the bar from both ends, trying to make the bar shorter. In this case we say that the bar is under compression. We're trying to compress the bar. We're trying to make the bar shorter. And so therefore when we talk about stress, we really talk about compressive stress. And again, it's the force applied on both ends. Of course, Newton's third law requires us to push with an equal amount of force on both ends. So we take the force on either end and divide it by the cross-sectional area, and that would then be the stress. Again, the stress is determined both by how much force you apply and over how big a cross-sectional area you apply it. The strain then is the deformation divided by the original size. In this case, this will be in terms of length. And so by compressing the bar, we're making the bar a little bit shorter. That's the delta L. Notice when we make it shorter, we tend to use a negative because it's decreasing in length. And that would then be the original length. So that would be the ratio of the change in length over the original length, which is called the strain. And again, the ratio of the stress over the strain, when we write it like this, is F over A divided by the change in the length divided by the original length. And we can ignore the negative for a moment. Just that ratio by itself is called the Young's modulus. Now, let's take a look at our second bar. In this case, we're pulling on the bar, both ends, and pulling apart from each other. Again, those forces have to be equal, Newton's third law, because if one was bigger than the other, the bar would accelerate in one direction or in the other direction. So for the bar to stay stationary, you got to pull both directions with the same amount of force. We now say that the bar is under tension. We're pulling on the bar, we're trying to make it longer. That's called tension. And therefore, instead of calling it compressive stress, we're going to now call it tensile stress, since we're pulling on it, the bar is under tension. So tensile stress is defined exactly the same way. It's force divided by area. And the tensile strain is the deformation, in this case the length, divided by the original length. Notice here it would be a little bit longer, so delta L is therefore positive. And if we find the ratio of that, stress over strain, it doesn't matter if it's compressive stress and strain or tensile stress and strain, the ratio means exactly the same thing and still will be the Young's modulus. The vast majority of materials, if not just about all materials, they have the same ratio of stress over strain regardless if you compress it or if you stress it in the opposite direction. So compressing or put under tensile stress, you find the same ratio. So again, to illustrate that ratio, we call that Young's modulus, and we'll talk a little bit more about that in a later video. But again, understand that the size of this ratio talks about, or the size of the ratio implies the strength of the material. How easily does it resist deformation? The bigger the number, the bigger the ratio, the more it resists deformation. The smaller the number, the less it resists deformation. So as an example, we have two materials, call it aluminum and call it brass. Aluminum here has a Young's modulus of 7 times 10 to the 10th newtons per square meter. Brass has a Young's modulus of 9 times 10 to the 10th newtons per square meter. So without going into the details, because we'll do that in the next video, a couple videos from now, we just want to look at those numbers, and can you tell from looking at these numbers which material resists deformation the best? And since brass has a larger Young's modulus, you could say brass resists deformation better than aluminum. So putting the same amount of force on brass and aluminum, aluminum will deform a little bit more, brass will deform a little bit less, as long as the force are the same and of course the length is the same. If the length is different, of course, then of course again, the ratio will still take care of itself. But I would say what's important is that we look at the compressive stress and that the force divided by the area is similar or the same for both, otherwise you can't compare them very well. But again, the ratio of the stress over the strain, you can see the result. Aluminum, not so good. Brass, a little bit better. But even though aluminum has a smaller number, that's still a really big number, and you can see you need a lot of force to cause any sort of appreciable deformation, even if it's aluminum. But this is just for comparison. And that's how you look at tensile stress and compressive stress.